So we're going to do 3 examples of this in total. This is the second one. Each time it's going to get a little bit more complicated. So this time we've got more than one force, but we can use exactly the same theory to find a resultant force and moment at B. And so we're going to basically replace all of these forces with a single force and moment at B that does exactly the same thing at B as all these forces together do. That's why we're doing all this. So when you get to complicated problems, you can reduce it down to a much simpler problem. We're going to do that first, so we'll get a resultant force and moment at B, and then we're going to replace that force and moment by a single force at the correct lever arm, that it gives you the same moment and force at B as all of these forces combined. So let's work through that. This one, everything's still aligned in the x direction, plus or minus x direction. The next example, we'll have a look at what happens when you've got x and y components. Doesn't really change any of the theory, it just makes it a bit more time consuming to work through the calcs. So let's have a go at this first. So part A, we want a resultant moment and a resultant force. So let's go for the resultant force first. So sum of fx, I've already named all or labeled all of the forces, F1, F2, F3. So it's just equal to F1 plus, well, let's do the sign right from the start. So I've also put on some axes here. And so I'm going to assume positive x is to the right, this is to the left. So therefore that's going to be negative F1 plus F2, because it's going positive direction. That's F2 up here. Negative F3, which is equal to negative 250 plus 650 minus 300, which is equal to negative 650 minus 550. So therefore it's positive 100 newtons, or in newtons. And then we want to find all, we could say, I'm just thinking here, the sum of fx, that's okay. That's the same no matter which point they'd asked us to use the sum of the forces. So suppose they'd asked us to calculate about another point C here, wouldn't change the sum of the forces. But when we talk about the moment, we have to be a little bit careful. The moment will be different for different positions. It's not a couple, so it'll change depending on the position that you take. So we're taking it B. So what I'll usually do for that is the sum of the moments, and then I'll put a B up at the top about B. You could put it at the bottom. Either way will do. And I might just put it at the bottom actually, just thinking. Sum of the moments about B is equal to, so the sum of the moments, well, it's just force times lever arm. So force 1 times distance 1. Let's think about direction again. And so anti-clockwise positive, so that one is positive. It's trying to rotate this way. This one here is trying to rotate the other way. This one here is anti-clockwise again. So that first one's positive, minus F2 D2 plus F3 D3. So the lever arms, well, the line of actions will be along this way. The lever arms are just the distance, the height up that post. And so don't need to do any more with that, I don't think. So that's just going to be 250 times the lever arm for that is 600 millimeters. We'll change it to meters. It'll come out to nice units, minus 650. So this one's going clockwise, so it's negative. 600 plus 600 is 1200, so 1.2 meters. And then for the last one, we've got positive, going clockwise, 300 times 3 times 600 is 1800, so it's plus 300 times 1.8 meters, which is equal to, it's just, I've already done that one, 250 times 0.6 minus 650 plus 300, it's minus 90. So minus 90 newtons, and we used meters, so minus 90 Newton meters. And so that's equal to 90 Newton meters negative, so it's going clockwise. Okay, and so what I'll do now is I'll probably just make a quick sketch of that. So just getting rid of all these forces and just showing the resultant on this. And I'll write out the answer, and then we'll move on to part B. So just give me 2 minutes. Okay, so written out my answer and drawn what that answer means. Now, what we can do here is we can simplify it even further. So you'll have seen this force is always the same no matter what point you choose to take your moment and force about. But it's the force is always the same, but the moment changes. Now, what we can do is we can move this force so that it gives us this moment, and that'll make it even simpler. We can get rid of this moment and we'll just keep the force. So let's think about how we figure that out. And this is part B, it's asking us for that. Part B is saying, replace the force a moment with a force and no couple. Not very well put, I might change that and I'll fix that. So what it's really saying is, we're trying to find a force, we want to know what the distance of that force is from B. So for force only, we'll call it Fr as the resultant force is 100 newtons. And the moment must be 90 Newton meters about B. So moment about B is equal to 90 Newton meters. So we can create that moment with that force because we know the moment at B is equal to Fr times some value of D. So therefore 90 is equal to 100 times D. Therefore D is equal to 90 divided by 100. Therefore 90 divided by 100, which is 0.9 meters. So we had somewhere up near the top, so that's, oh no, that's not really, it's quite low down. Yep. Just trying to think the best way to steal this. So what we're saying is, you could replace these. Can I get rid of them easily? That's the question. Let's have a look. Looks like I can't. So rather than do that, what we could do is we could just apply a 100 Newton force with a lever arm of 0.9 meters. And so it's going to be something like, just trying to see where that 600 went up to, so it's halfway up the 600, so it's somewhere just below here. And you've reduced that whole system of equations to a single force. And as far as B is concerned, as far as B is concerned, it makes no difference. You're still going to get the same force and moment at B as you would for all of these forces combined. What does change is the force is higher up. So you'll see here, you've got a force applied here. So this is going to be, it's trying to push this sideways. You don't have that in this situation. So you can't use this simplification to analyze part of the post that's up here. But as far as B is concerned, all of these different systems, these three different systems are all the same. Now I just need to be careful with this. That's in the right direction. So just looking at that, so that was that way, and I've still got the moment from this force is still in the same direction. So we've got it in the right direction. Oops. Is that all done? So just to reiterate, we're just combining all these forces and we're looking at this point B and we're just simplifying those forces so that it doesn't change what's happening as far as B is concerned, this point down here. And so we've found two things that were similar or the same as that as far as B is concerned. You could apply 100 newtons in the positive x direction with a couple or a moment of 90 Newton meters clockwise, or you could just apply a force of 100 newtons. Haven't really fully explained or haven't fully drawn it in my sketch here. What's the best place to draw that? Probably over there. Because I've told in the sketch I've given the force, but I haven't given the lever arm. And so applied a lever arm here. and that was 900 millimeters. I think I may have said 90 before. It was 900 millimeters, sorry. Okay. And if you were to calculate the sum of the moments and the sum of the forces about B for all of these different arrangements, you'd find that you get exactly the same thing. So if you're unsure of any of this, go back through it and just calculate sum of X components, sum of Y components, and the sum of the moments for each of these different situations. You'll find that they're the same for all of them.